Hi guys, we are doing related rates, which is unit 3-5 in the Essentials of Calculus. So let's get started. What is a related rate? Well, basically, a related rate is a story problem. And I know you're like, what? Story problems in calculus? That's not fair. And I'm like, yeah, that's what calculus is all about. Story problems. Actually, no, calculus helps us solve so many things, and so really calculus is all about story problems. This is why we learn all of this other stuff, because calculus is really applicable. In fact, it's like more applicable than some of the other like math you've learned so far, because you can really solve actual real life problems that happen instead of like these hypothetical situations where everything is perfect like we did in algebra. So let's get started. Let's take a look at what a related rate really is. Well, so make myself small here. So basically, a related rate is an idea that you find the rate of change with respect to time of one quantity by using the rate of change of a related quantity. So I know that sounds like ridiculous, and how are we going to do that? But basically, think about this, okay? So related rates could, a really common example is this, like filling up a cone. And we could say, like, as time increases, we slowly fill up the cone, right? And we're looking at how the height changes. This function right here is giving us a, uh, um, a a representation of the water level, because see, the water level at the when time is very small, the water level is rising really quickly because the cone doesn't have a very big radius. But as it gets bigger, see, the water level rises less quickly because it has a bigger radius, so it takes longer to fill up. Um, and so basically what we would do is we would find um, the rate of change of the volume with respect to time, by finding also the rate of change of like the radius and the rate of change of the height and things like that. So there's going to be a lot of different like pieces and parts that go into this. So I just want you to imagine like how we would find the derivative of something like this. And you might think about the fact that the volume of a cone, the equation for the volume of the cone is volume equals pi over 3 r squared h, right? So it's pi over 3 times the radius squared times the height. And so we would take that formula and we would differentiate it with respect to t, with respect to time. So let's look at what some slightly simpler ones would look like in our notes. And then we'll get to those little bit more complicated ones here in a bit. Okay, so again, remember we're talking about the rate of change with respect to time, which means that our independent variable is always going to be time. It's always going to be t. So our input is always t. Just like in most of our functions before, we've been taking the derivative with respect to x. So x is our independent variable or our input. But in this case, we're saying as time changes, how does the rate of change, or what's the rate of change of the area, or what's the rate of change of the radius, or what's the rate of change of the height? So we're trying to figure out what is how are some of these other things changing as time moves forward. Okay, so we're almost always going to be, well, actually not almost always, we are always going to be with respect to time. Okay, so related rates always is differentiating with respect to time. Okay, so this is kind of like the little formula for doing related rates. This is the step-by-step of how we do it. So first we draw a picture. So we can picture it. Like if we're talking about a cone, I would draw a cone, because sometimes it's hard to picture. I remember a related rates problem that I did with a cone. I started it without drawing a picture, and then after I drew the picture, I realized, duh, the radius changes, and it didn't dawn on me that the radius changed in a cone as time, as it filled up. So that was cool. So I just had to draw that picture to help me figure that out. So then we write what is given and what is to be found. Okay, so we're going to be given a lot of information, like different values at different points, and we use our d dt symbols because remember, we're differentiating with respect to time. Then we write an equation relating the variables. So if a quantity is changing, it must be represented with a variable. So think about what is changing and what is staying the same, right? So in a cone, we'll use that example again. In the cone, the height is changing, the radius is changing, and the volume is changing, right? As I fill that up, the volume, the height, and the radius all change. So those kinds of things would need a variable. So, V, R, and H. If the quantity is a constant, it must be represented with a number value. So, like in our function or in our equation for volume, pi over 3 never changes. So it would just be a number value. Okay, so if something is not changing, it's a constant. If something is changing, it's a variable. Okay. So then sometimes you're going to look for secondary relationships between quantities to reduce the number of variables. So for example, if it says the height is always twice the radius, then instead of having an R and an H, we could just relate one of those to the other. So we could say like, well, R or H always equals 2R. So everywhere we had an H, we could put in a 2R because now we only have R's instead of R's and H's because that's just less complicated, okay? And then, I got myself a cold. Anyway, then we substitute in values. Oh no, then we implicitly differentiate. That's the important step. Here we do the implicit differentiation to both sides with respect to t. So when we'll look at our things, you'll notice that oftentimes you won't see a t. We don't have t as a variable. But we're differentiating with respect to t, and that's where that implicit comes in, right? Because we're differentiating a function of t, okay? And then finally, we're going to substitute in number values and solve. So some of the things you're going to need are like these geometry formulas right here. So these are some things that we're going to talk about a lot because we're talking about volume and area and stuff like that. So just this is a good reminder of what these different formulas are. So let's take a look at some pretty simple examples at first. And they're kind of abstract, so don't freak out if they're just a little bit challenging to think about. Okay, so first we have these examples, the first 3 steps are already done for us. So they've already drawn a picture, which we don't need. They've already written out the equation for us. So all we need to do is we need to do steps 4 and 5, which is implicitly differentiate and then plug in things to find our final answer. So this is saying, given that the area equals s squared, and then this information like ds dt equals 3 and s equals 4, and then we want to find the change in area with respect to time, right? That's what dA dt means. I want to find the change in my area with respect to time. Okay, so we have this equation, and remember a is a function of t, and s is also a function of t. So anytime we differentiate them, we're going to have to use implicit differentiation to do that. So to find the derivative of a, let's just differentiate both sides. So that would be dA dt equals s squared, so we differentiate s squared, which gives us 2s, but then remember, s is a function of t, so we have to use the chain rule to tack on that ds dt at the end because we're differentiating with respect to t, okay? So we differentiated this equation now, and all we have to do is we have to find what dA dt is. And it's given us some information, and in implicit differentiation, you're going to be given a lot of information because right now I can tell you this is the equation for the change in the area with respect to time. And I can tell you this is the change in s with respect to time, but I don't actually know what those values are. So I couldn't right this second say like, oh, well, the the change in area with respect to time is this, because I can't see that from this, right? So I am going to just fill in what we're given. So if I can get my technology to work for me. All right, so we don't know dA dt, but we do know that S at this point equals 4, so we can go 2 times 4. Oh man, that did not show up at all. Okay, let's try that one again. 2 times 4. Wow, that is terrible. This is almost as bad as my smartboard. All right, let's try one more time. Let's see. Okay. 2, oh, I have to put my pen back on. 2 times 4. There's like this spot in my tablet that just doesn't want to work. All right. We'll do it up higher. Okay. 2 times 4. And then we also know that ds dt equals 3. So it's times 3. So what is dA dt? Well, it equals 2 times 4, which is 8 times 3, which equals 24. Okay, so that is one quick thing